Good morning, everyone. The recording has started. I think we should be good to go now. Welcome to today's webinar with our very own Marcus Hayes Nielsen. For those of you who I haven't met yet, my name is Jessica Kaylin Parsons, and I'll be facilitating today's webinar titled Navigating Complexities of PVT, Data Management, and Digitization. So before we go into the presentation, however, I'm just going to go through a few meeting logistics. First off, as you guys would have noticed, everyone is muted today as we have hundreds of registrants, which we're excited to have here, who will probably be coming in and out. Secondly, we plan to break this webinar into two parts. First will be Marcus's presentation for 30 to 45 minutes, and then a 15-minute Q&A period at the end. Please use the Q&A chat box for all of your questions, or feel free to send me an email at jessica@whitson.com if you can't seem to find the chat box. The webinar itself is facilitated by us here at Whitson. If you don't know Whitson, we are a shop extremely passionate about everything petroleum engineering, whether through our software platforms Whitson Plus and Whitson PVT, or through our immense amount of training and educational courses. We actually just added a few more trainings to our site last week, so feel free to take a look at whitson.com/trainings. And as always, these courses are complimentary for Whitson subscribers, so you should see a separate registration link on those courses now, if that applies to you. Now over to our presenter, Marcus, who is our Whitson PVT product manager and an expert on everything PVT. He is a University of Oklahoma and Norwegian University of Science and Technology alumni, both a reservoir engineer and a software developer. And through his interactions with PVT experts and everyday users of PVT data and models, Marcus has really developed a unique perspective of how these models are created and applied in real-world settings. So Marcus, over to you.
All right, I'll take over the screen here, and hopefully that works fine. All right, so yeah. We're going to be taking a little bit of a So we're going to be taking a little bit of a look at the some of the complexities that come with PVT data management and the digitalization part when it comes to PVT. And it's by no far extensive, but we'll at least give it a go, and you'll get a bit of a flavor of the challenges and some of the tips and tricks that we've learned here over the past years. This is just a little bit of a slide about myself. I was, Jessica already introduced me, so I don't need to go into that. I'm pretty active on LinkedIn with this PVT stuff. So if you do enjoy this, then feel free to check me out there. But I want to get straight into the topic here. And basically the idea is that we want to look at PVT data management, right? Which is a huge issue for not just one company or two companies, but every company that has any sort of fluid data, which is basically all operators, right? So let's just imagine that we have some oil company, right? And they're going to have multiple employees like Alice here, Bob, and Carlos, for example, A, B, and C. The way that it's usually structured is that, let's say Alice, she has her folder on her OneDrive or her computer locally, where she has a bunch of PVT reports stored locally on her computer. Similarly, you're going to have Bob has his and Carlos has his reports, and they might be in different formats like PDF, even sometimes pictures like a PNG or Excel files. And if we took all of those files and we looked through all of them, then we could potentially organize those files, and we would see that in reality we only had 4 PVT reports, even though they had a total of 8 or 10 separate files on different locations on the different computers, right? So that's a huge step even there. If you're able to centralize just the raw data reports that you're getting from the laboratory, that's great. That's an amazing first step, right? And then with those kind of raw data points, what we can do is we can take those reports painfully, and painstakingly take them through a digitalization process, and then hopefully get them into some sort of a digital format. Now, we have our solution for Whitson PVT, and then there are other solutions potentially out there on the market. But the main thing is that the ideal situation is that we have a common platform for Alice, Bob, and Carlos all to interact with to get their digitized and kind of easily available data that they can then take and use for developing models, doing predictions, and so on and so on, right? And this is kind of the system that we're going to take a look at today. We're first going to take a look at the database structure a little bit. And then we're going to take a look at PVT reports because they can be quite challenging in and of themselves. And then we're going to take a very specific example of how we can take a PVT report and digitize part of it. So that's going to be the third topic. And then at the end of it, we'll have I'll open up for questions, and then you guys can ask me all the tough questions that you have. All right. So when building a PVT database, it's very important that we kind of have an understanding of the hierarchy of how the data is going to be stored, okay? And what I'm going to do now is I'm going to give my perspective, our perspective from developing Whitson PVT, and using that and kind of sharing with you why we think it makes sense, okay? So let's say we have a system like this. I'm located here in Norway, so a lot of our fields are offshore, off the Norwegian continental shelf here. So let's say that we have 4 different fields, A through D, and they're all producing to the same common platform, okay? What we recommend doing is basically grouping all of these 4 fields into what we would call a multi-field region, all right? This could be as wide as a basin, like we have for the unconventionals in North America, like we have the Eagle Ford Basin, and we have the Duvernay Basin, and so on. Or it can be just a couple of fields that you have ownership over in the Norwegian continental shelf. Then if we zoom in a little bit, and then we zoom in a little bit further, then we see that we have inside of field A, we might have 3 separate wells, which are kind of indicated here on the screen, which are commingled into a manifold like this. But within that field, we might have different regions, okay? So we might say that this bottom part here is the south part of field A, while this upper part here is the north part of field A. And we should be able to, together with that field, basically identify which region of the field we're in. Then if we take a slice along this one well here in the middle, the system might look something like this, okay? So we have our cut going from right to left here, and that's also the same going from right to left on the figure. And so we have our south part of the field A here, and we have the north part of field A on the left. And within a field, we have potentially have different sands or formations or layers, depending on the terminology that you use. Our terminology is formation. So we might have the upper formation A on top of formation B below it. Now the formation of interest in our case is this upper one, formation A, and it actually might be subdivided into, okay? So you have formation A, and it's the upper part of that formation. And then you might have a central zone and a lower zone. And all of this information is potentially very important in understanding the fluid phase behavior that's happening down in our reservoir. We might have one formation, the central one, which it's locked off from the other 2, and it could have potentially very different PVT properties, being more aromatic or more paraffinic, and that could have an impact on how we're going to develop our equation of state model. Then let's say that we're taking some samples here down along the well, and when you're taking the sample, like an MDT type sample, then you might collect it, and then you're going to give it certain properties. So within the field, within the formation inside of that field, we have a specific, we have some general information about that sample, which is tied to that well. It's going to have some general information like the location, the geology, the fluid type, the sample type, the pressure conditions when you took the sample, and so on. You're going to have compositional data, most likely, if it's an MDT type sample. And you might potentially also have PVT experimental data. And all of this should be linked to that sample, which is linked to the well inside of a field, potentially from a specific zone in one of the formations in that field. So having a good understanding of the hierarchy, like I've kind of quickly gone through here, is the first step in building your database structure. Do you want your region only to be a single field? Do you want it to be multiple fields that are commingled together? Do you want it to be a business unit or an entire basin? Those are all decisions that you should make as early as possible when trying to build a database. All right, so with a little bit of understanding of the kind of the hierarchy of the system, and if you didn't catch on, then we'll make this recording here public so you can check that out later. With that a little bit in mind, then we can move on to the next part here, which is going to be the PVT report itself. And what I've done here is taken one of the PVT reports that we own from one specific lab and from one specific sample. Now, I'll just make the caveat here that this is not to put that specific lab down or to say it's good, bad, or ugly. It's just an example, and it shows all of the complexities that are reflected in most PVT labs or lab reports out there. So the specific report that I'm going to be looking at is this one from Schlumberger up in Canada. It's from the Duvernay field, which is an unconventional field in Canada. It's a 51-page report. And there's only one recombined sample, and that recombined sample has a set of PVT experiments inside of it. So for a single sample, we have 50 pages of a report, and we're going to try to break that down to try to understand this a little bit better. And I'll send this to you, Jessica, so you can send it out as part of the follow-up to this. All right. So if we break this down here, we can basically divide that 51-page report into 4 subsections. Okay. The first one is the front page. Okay. And the front page is often very useful. And in this case, this is the page where it's telling you what I don't know if you can see my cursor or not, but let me put the laser pointer on. This is where you can see the well, and you can also see the date of the report, which can be very useful, and the report number. Now, we always recommend making a note of what the report number is. And the reason for that is if you're going to go and contact the lab after the fact and you want to ask them a question about this specific lab report, then attaching that report number is also often a very useful thing to have when sending them an email. Okay, so even on the first page, there is some useful information. It also tells you the field, which in our terminology would be the basin. And yeah, so that can be a little bit tricky with the terminology. Moving on to the second part, which is the info pages. Okay, and so this is from 2 to 6, those 15 pages of information. And what I've done is just very top level subdivided them into the executive summary, the sample inventory, and the additional information pages, which is a lot of. Okay, and on the executive summary here, it tells us a little bit about what was done throughout this whole procedure of sampling. And from this, we can learn that there's basically 4 rounds of separator samples that have been taken, separator gas, separator oil samples, and pairs. So 4 pairs of separator samples, and you can learn about the process that was done when taking the sample. Okay. And then it also has some summary information here, which is typically just repeated information, which is going to come further down in the report. And the second part here, the sample inventory, has a little bit more information. It tells you some more about how the samples were collected, something about the conditions at the laboratory. But the main thing here is that it has a list of all of the separator gas and separator oil samples that were taken and what the conditions were when those samples were taken, basically. Okay, so this kind of top level here is also going to tell you which one of the separator gas and separator oil samples were physically mixed to give you the separator recombined sample, and that's going to be found somewhere in these other pages here at the end. So it's always good to have an understanding of what was actually done in the laboratory, and this is kind of giving you a soft introduction to that. This is usually where we have to do most of our detective work if we can't find something. Okay. Once we're done with the info pages, we can move on to the third part here, which is going to be it's called tables and figures in this specific report. And it's basically divided into 3 subsections. The first one is the compositional data. Okay. So this has all of the compositional information for every single separator gas and separator oil sample that was taken that we saw in the sample summary page. So that's going to be 4 times at least 2 sets of separator gas, separator oil samples. And it also tells you what the mathematical recombined composition is for that separator recombination process. The second part here is they've done that physical mixing of one of the separator gas and one of the separator oil samples. They've recombined it at some GOR, physically mixed it, and then they've taken that PVT cell and done PVT experiments on it. And that's where that information is. And then something a little bit peculiar here at the end is this simulated data. Now, I'm going to zoom into this a little bit and see. This is one of the first pages that you see in this simulated data section. And we typically never recommend asking for this because A, it costs money, and B, all that it is a tuned equation of state model matched to very, very limited data, typically only the saturation pressure, which you can see here. This blue dot is the only thing that's measured on these two tables here. So you're getting kind of a very uncertain data set of simulated points. And it might be, a pretty picture to put in a slide, but it definitely doesn't represent your actual reservoir fluid phase behavior because it's too limited of a data set. So we typically don't recommend asking for this data and don't typically recommend using this data for anything other than potentially looking at it to see if it looks nice, I guess. But it's not worth spending the $1,000 it costs to add this on. And then the last part is an appendix. And this is usually a generic appendix for that specific lab. And they will tell you about the equipment that they use, what type of PVT cell that they use, what type of chromatograph, detector, and so on they use. And it's very interesting to read if you want to go into the weeds, but it's not for everyone, and that's fine. So as you can see, there's quite a lot of complexity even just in the report. And this was a report for a single sample. Sometimes you will have reports for not one sample, but 5 or 10 or 15 different reservoir samples, MDT samples, mixed with separator samples and all these other stuff. So it can get really complicated and really long very quickly. Then we get to the biggest challenge of them all, which is actually taking these PDFs, Excel files, or pictures, sometimes even, and actually digitizing these into a digital format that you can use for simulation or plotting or a bunch of other things. Okay, so the data digitalization starts with our sample again. And for a sample, we're going to have the 3 types of information. The general info, which I talked about, is basically putting that sample in the hierarchy that we looked at in the beginning. And then it's going to have compositional data, right? It's always going to have compositional data, because if you don't have a composition, then you can't do anything, any compositional simulation with it. You can't match the PVT experiments if you have that. And then the last part is the PVT experimental data. And just to give you a little bit of an idea of how complicated the process of digitizing a PVT report can be, I'm going to go through adding the compositional data for one separator recombined sample for the report that we just looked at into Whitson PVT. Okay, so I'm going to digitize a separator recombined sample. And before we get to the data and the pages and where to put everything, let's just see if we understand the process that the lab goes through when they have a separator recombined sample in their laboratory. So you have your well, and it goes into a test separator. Okay, so usually a single stage separator to some higher pressure and temperature. And it's going to have some sort of a producing gas oil ratio, usually stock tank cubic feet per separator conditioned barrels, right? And then it'll take a sample of that separator gas, and it'll take a sample of that separator oil. Usually not one, they'll do 2 or 3 in a row. Okay, but let's say that you just took one of each for this case. This separator oil, if you want to get the compositional data for that, you can't measure that directly, or at least we don't measure that directly. What the lab will do is they'll actually take that separator oil, they'll take out part of it, flash it to surface conditions, and you'll get a flashed gas and a flashed oil composition from the separator oil, which will have its own GOR, recombination GOR, and it's going to go to surface conditions. And then we can measure the composition of these and mathematically recombine them to get an estimate of the separator oil composition. Then what the lab will do is they'll take the remaining separator oil and separator gas, and they will physically mix those two at some volume ratio in a PVT cell, okay, to try to honor this separator GOR here on the left. And they might hit perfectly, and they might miss slightly, okay? Now, as a validation step, what is sometimes done by the laboratory is that they will actually take out part of this physical mixed fluid here, and they will flash this to surface conditions to get a new flashed gas and a flashed oil composition, which they can measure or at least estimate. And then they will mathematically recombine those to get a second independent estimate of the physical mixed fluid composition. And why do we care about that? Well, there's 2 goals for getting this composition. The first one is to try to estimate what the well stream composition is that's coming into the well, right? Or into the separator. But the other goal here is basically to get an estimate of the composition in that PVT cell, right? So that we can use it for fluid model development, right? To try to predict the PVT experiments that cell goes through. And the things that are actually measured here is going to be your flashed gas composition and molecular weight, your flashed oil composition and density, right? And then we're going to get the compositions of these flashed compositions down here from the separator oil. And then we're going to get the separator gas composition measured. And then from this, the lab will do a mathematical recombination from the left and potentially from the right. And they will get two slightly different compositions for the same physical mixed fluid that we're doing our PVT experiments on. And that can be very important, or it can be not important at all. The only way to know if it's important or not is to test both and see which one gives the better prediction with the equation of state model. All right, that's a bit complicated, but basically what I want to do is I want to emphasize that for a separator recombined sample, there's basically two types of compositional data structures that you can have. You can have what I call a separator recombined sample, which is this process on the left. So we're taking the separator oil and separator gas compositions and mathematically recombining those. Separator oil then having its own flashed oil and flashed gas, which has to be mathematically recombined, right? Or you can have a single stage flash composition as shown here on the right. The moral of the story, it's pretty complicated, right? It's not a straightforward procedure. And usually what you see in the beginning of the lab report is just, this is the recombined composition, don't ask any questions. But if you don't know which way it's been done, then you don't know what the uncertainties are and you don't really know how to tackle it. How do we digitize that? And what I'm going to do now is I'm going to use Whitson PVT as an example database structure. And I'm going to try to show you how I filled in the data in Whitson PVT. I don't know if you can see it or not, but I basically have the same information here for this separator recombined sample as I showed in the plot before. I have the recombined fluid composition. I have the separator fluid composition here. And then I have the flashed fluid information from the separator oil. And then I have a bunch of data here on the left, like the recombined fluid molecular weight, the recombination GOR for the separator gas and the separator oil, and then some information about the separator fluids, and there's even more information below. And I just want to show you the process of filling this out. So the first thing I'm going to do is I'm going to go to page 30, and I'm going to find the recombination GOR up here. This is the mathematical recombination GOR for the separator gas, separator oil, that was used to take that separator gas and separator oil composition to get that recombined composition. And then we also get calculated molecular weights for the separator gas and separator oil here, not measured. How do they calculate them? Another topic for another day. Yeah, and then you can see we can put in the composition of the recombined fluid here, because it's got the component slate, the molecular weights, and the recombined fluid mole composition. And there's no mass composition here, so we're just going to leave it empty. Then we can go to page 12 to find some information about the sampling conditions. And if you look here, we want to have the separator conditions when the samples were taken, so we can do the Hoffman check and all this other stuff. And the issue is that if you look at the sampling pressure and temperature, the separator gas and separator oil were actually taken at different conditions. The separator gas at 130 psi, the separator oil at 120 psi. So we have to make a choice which one we want to put in. And so I put in 130 here. I might make a note about that to say that it might be the other. Then, if I want to get an estimate of what the fluid molecular weight is and the oil density, they don't give it anywhere in the report, even though I know for a fact that the separator oil density has to be there, because that's part of how they do the mathematical recombination. So I had to set up an Excel file externally from the PVT report and find these two numbers myself. Okay, I had to put on my PVT detective hat, and I had to calculate these numbers or estimate these numbers based on the other available data that I had. Now, you don't have to, but if you want a complete data set, then this is kind of what you have to do. Okay. If we move over to the separator fluids here, you can see we have the separator gas and the separator oil compositions. And we can find the separator gas composition on page 27. And having looked in the beginning of the report, I know that it's sample number 2.08, which is the actual separator gas that was used for this mathematical recombination. So I can put that in here. And if you notice, it has a composition that goes up to C12 plus, right? And it's got the mole composition and the mass composition in the different order than what we have in Whitson PVT. And then we can find our separator oil composition on page 28, and we can put that in, and you can see that goes all the way up to C30 plus. So we have a discrepancy in the component slate. Then we can keep scrolling down, and we can see that from page 29, this is the GOR for the separator oil. Okay, so when we took that separator oil and flashed it to surface conditions, we can digitize that, and we can see it has a GOR of 5 point something. And it doesn't give you the units. It just says it's volume per volume. Okay. And what that means is that it's SM3 per SM3. And we can also find the gas-specific gravity, and we can find the oil, the flashed oil properties coming from the separator oil. And you can see that the flashed oil density is measured. It always should be measured, but the flashed oil molecular weight is calculated. How do they calculate it? A different story for another day. They basically just assumed a set of C7 plus component molecular weights, and they did some calculation. And then to get the gas molecular weight, we go to page 28 again, and then we can scroll up, and we can move over to the flashed gas and flashed oil coming from the separator oil. And you can see that's coming from page 28. And here we just have to plug these in with the C30 plus component slate. Now, we always recommend putting in the component slate with the most amount of detail possible. So if you have a C30 plus component slate, good, use it. If you have one that's C12 plus and one that's C30 plus, you have to live with it, or you can have a software like Whitson PVT that will do that splitting and conversion for you, the slate to slate conversion. After having done all of this, we're done with adding the compositional data for that one sample, basically halfway, right? Because we also have the single stage flash that we could add as a secondary set of compositions, right, for the same mixed fluid. So to summarize, for this one sample, we had to go to 5 separate pages from page 12 all the way to page 30 to get the information that we had to put into our database. Plus, we had to make an Excel file to guess, or to basically to estimate what that separator oil density is. This is not an easy process, right? And you might have some lab reports which makes it a little bit easier, some lab reports that make it a little bit harder. But at the end of the day, it's not a trivial task to do, and it takes patience and it takes effort to do. Okay, so now that we've seen how complicated it can be, I wanted to show you a couple of ways that we like to quality check the data that we get, right? So now we have a little bit of an idea of the hierarchy. We have an idea about the PVT reports and the complexities inside of it. And then we have an idea of how complicated it can be to go from the reported data to a database structure. So let's do this quality check here. We typically recommend looking at the data QCs from 4 separate angles, okay? You have the data entry QCs. Everybody's human. It's very easy to make mistakes, especially when you're adding a lot of data. It's not a lot of fun. So it's very easy to get careless and make mistakes. So having good data entry checks is very important. Then we have what I like to call the single sample quality checks. And the single sample QCs is probably what most people think about when they hear PVT data QCs. And we'll take a look at that in a bit. Another thing that you can do, at least in Whitson PVT, very easily is if you have a lot of data, plot it on top of each other to try to highlight some of the issues in the data set, or to try to quality check individual samples by looking at them in a trend. And the last part here, which is sometimes overlooked a little bit, is just try to simulate the data that you have. A default Peng-Robinson is not going to be 1,000% off on your saturation pressure. So that might indicate that you've made a mistake there, right? So we're going to take a quick look at each one of these here. And we're going to start with the data entry QCs. And I'm just going to show a video where I have compositions here on the right, and I'm going to copy paste it over to Whitson PVT. But notice that we actually have the mass amounts and the mole amounts in an opposite direction from what we have in Whitson PVT, so that when I copy it and paste it into Whitson PVT, they're going to be in the wrong order. But luckily, we can use a little bit of physics to double check this, because we know that that the mass amount of the heaviest component should be more than the mole amount of the heaviest component, because by converting from mole to mass, we're multiplying by a very large molecular weight, usually like 400 or 500. So we can do these quality checks when you're entering the data and giving you a warning saying that I think you should have switched these. And once you do that, you can just hit switch and save. And then you can potentially plot the data as well, just to have a sanity check to make sure that everything looks okay. So this is what I mean by data entry checks. This is like you were not thinking and you weren't actually looking at the data. If you can catch these things, it's very useful when you're entering the data. The second part here is the single sample QCs. I'm going to divide that into two parts, okay? The first part is a set of equilibrium checks. And I think the most commonly thought about one is the Hoffman plot. And this is something that a lot of people do when they have separator gas, separator oil samples, and they want to see, were those two fluids in equilibrium with each other when the samples were taken, okay? That's kind of what the Hoffman plot is telling you. The second type of check or group of checks is basically the material balance checks. Okay, and there's a bunch of different material balance checks for the different experiments, for the different types of data and so on. But at the end of the day, I'm just going to show one example, and this is from the DLE. And the idea here is that we measure something at the beginning of the experiment and at the end of the experiment. Okay, so like in this case, we have an independent estimate of the initial fluid composition, and at the DLE, we will typically measure the composition at the end. And we can use the mathematical process of, we know what the composition is that we took out. We can calculate that new oil composition at the next stage. And then we can mathematically remove the gas composition that was taken out. And we can do this all the way until we get to the residual composition calculated in a forward material balance perspective, okay? And then we can compare these two, the lab measured versus the calculated. And this is the material balance check. And an example of this is shown here in Whitson PVT, where we have for this separator recombined sample, we're doing the Hoffman plot here. You can see that over here on the right. And then for the CVD, just like for the DLE, we can also make this forward or backward material balance check, depending on if you start with the total composition and go down the experiment or in reverse. It's basically kind of the same thing. And you can check if there's a difference between those two compositions. And like in this case, it's a very small difference. And so it's not going to have a big effect potentially. That's the single sample QCs. The multi-sample checks is relatively straightforward. You just take all the samples that you have. And here I'm just using our GIS functionality in Whitson PVT to lasso select all of the wells that I have in the Duvernay field. And then I just click plot here. And what you see on the left is the plot of the relative total volume versus pressure. And we have one curve which is sticking out from all the others and has a much higher, apparently, saturation pressure than all of the other fields nearby. And so what we can do is we can click in there and we can go to the PVT experiment for that sample. And what we see is that I forgot to change from bar to PSIA. And so if I go and change this now, then I can basically just refresh the plot, and now everything is going to fall in line here on the plot on the left. So this is just a very simple example of how putting multiple data sets on top of each other can really help with QCing the data that you have. The last part here is basically just taking the data that's gone through all those previous checks and just trying to simulate that one sample with a PVT with a simulation run. And that's what I've done here. You can see that my saturation pressure, the calculated saturation pressure versus the reported saturation pressure are very close, okay? So I'm matching the data within 0.5%, the p-set. I mean, that's pretty good, right? When I investigate a little bit further, I go in and I look at the actual PVT experiment. I see that my relative total volume is a bit off. It's kind of shifted to the right, which is a bit suspicious because the relative total volume should be one at the saturation pressure, but it's clearly not here. Then I can go to my DLE and look at the BOD value, and I can very clearly see that it's not hitting the saturation pressure any good. So why is it telling me that it's matching the saturation pressure within 0.5%, but it's mismatching very clearly from this data set, okay? So I can alt-click and open up a new tab, take a look at this sample, and then I can go to my CCE. And what you'll see here is that the saturation pressure is identified at the wrong pressure step. And then I can go down and I can fix this issue, save that, and go back to my tuning, rerun the simulation. And now everything is going to be falling in line much, much better here. Okay. So you can see now I'm getting a better match. this is a very easy way to kind of quality check your data. Okay. So with all in that in place, I think this gives you a little bit of a feeling for how we can do the PVT data management and how we can do the digitalization effort and how complicated it can be and how important it is to have good tools for the job. Just to end here before, and I'll let you guys ask some questions. What have we learned? Always important when you're going to try to build a database that you have a good understanding of the hierarchy of this PVT database. And PVT reports can be complicated. That's just how it is. I still open up new reports and have to go to my colleague and ask them, hey, like, can you help me try to figure out what's happening here? And that's just how it is. And you have to go back and forth and flip through the report to find all the useful information that you need. And digitizing this data, it isn't straightforward. It's easy to make mistakes. And having good tools for this is really, it makes the job a lot easier. And built-in QCs for data entry issues and for sample QCs. No matter how you end up doing it, it's very important. And the last thing here is that just there are multiple ways of doing this QC. It's kind of what I was talking about here at the end. There's not just the material balance on the DLE, right? You can have your DLE pass the material balance checks, but have crazy values somewhere else that you didn't catch just because it's not part of the material balance. So try to check in as many different ways as possible, because that will help minimize the issues that you encounter when trying to predict the data or make models or use those data sets for anything. And with that, I'd just like to say thanks, and I'll open up for questions here.
Marcus, I think this is the first time ever we have 0 questions.
I
feel like that is a testament. I think that is a testament to how great of a presenter you are. I just double checked the Q&A in the chat and no questions.
Well, then I'm always available. If you want to reach out to me directly, either on LinkedIn or via email, then you can find that. Was there a question that came in now, or is that no? Oh, let's see.
There we go.
There you go.
Oh, 3 just came in now. Everyone's coming in now. Thanks, guys.
Yeah. What is the default reservoir fluid, the separator recombination, or the SSF? Yeah. So since the lab is always going to be doing for separator recombination or for separator sampling, you're always going to have a separator gas and a separator oil. And they will typically always measure the compositions for those to do the Hoffman check to see which ones they should put together in the lab. So those are, I think, the most common. And then the single stage flash version of that is it's more of a validation step. That being said, some reports will only give you the single stage flash and not the separator gas, separator oil recombination. So it really depends on the lab, but I would say that the separator composition is the most common. Good question, Logan. Yeah. So what about if you're missing wax from the samples? So wax can be a tricky thing, right? Because if you have wax coming out of solution, if it's happening in the downhole, like so that the wax comes out of solution when you take that sample and transport it from the sampling point to the laboratory, then the lab can treat the sample to heat it up and take care of any of those issues, right? For certain fields, you'll actually get wax coming out of solution in the separator, like in the Montney, right? Even for gas condensate. And if you have wax coming out of solution in the separator, that can be a real issue, because then you might have some samples from the separator oil which have way too little of those paraffins in it, so it's going to look much more aromatic, and some that might just get a big lump of wax along with it, and it's going to be much more paraffinic. And so yes, wax can be an issue, especially for surface sampling, where the temperatures are usually much lower. Yeah, I don't know if that answered your question or not, John, but hopefully that was okay. And then how do you digitize the data? Are you using LLM? I wish it was easy to just ask, to throw my PVT report into Chat GPT, GPT, and just get it to spit out, a digitized version of the data. But so far, it's not been a very successful endeavor. I think it's very hard, right? Because different labs have very different ways of reporting the same data, different terminology, different pages, different formats. Even the same lab, different locations or vintages can be dramatically different. So right now, it's a very manual process, digital process. But as I said, if you have the right tool for the job, like what we have in Whitson PVT, it makes it a lot easier to do that digitalization process much more efficiently. I saw there was a couple of questions here as well. Quick one: is your software capable of generating multi-sample EOS models commingled flows? Yes, definitely. And in fact, the model development, yes, it gets harder when you have multiple samples commingled from multiple fields, but it becomes more unique. And that's one of the things that we've seen over the past years while developing the software tool, is that yes, we can make single models for multiple fields commingled into the same platform. We've done it multiple times here in Norway and across the world historically, but yeah, for sure. Good question. And then can you give some real case examples of fields where significant compositional gradient exists and are publicly available? I would recommend Lars Heer's PhD thesis. I think that's public. I'll double check with Curtis as he's on the call here. There's a couple of papers from the folks at Shell where they saw this compositional variation. In fact, they showed that you can actually have a gradient in how paraffinic or aromatic your fluid is, along with the compositional gradient. So Jessica, if you make a note of that question, then I can send some papers to follow up on this. And yeah, it's a good PhD by our friend Lars Heer. Yeah, good question. Was there anything else on the Q&A here? Let's see. It's a bit slow on my end. Can you see anything, Jessica?
Yeah, it's just loading slowly for me as well, actually. Yeah, there's quite a few new ones on there. So I'll start with Turker Karaman. I apologize if I said that wrong. Which data do you prefer to use in reverse calculations? One from flash liberation or differential liberation?
Yeah, so for QC purposes, we do both, right? If I'm understanding the question correctly. We always do both forward and backward material balance just because it's built into the software product. But like the more stages you have, the more potential sources for data uncertainty come in. So if you have 10 recombinations happening in 10 stages in the DLE, then you're going to have more potential sources for compositional uncertainty going from that residual oil back to the initial fluid that you have, right? And that's also the case when you have a separator recombined sample versus a single stage flash recombined sample for separator samples. But yeah, in general, we like to do the QCs on everything. And then was there any more here?
I think the other ones were also mentioned in the chat there. Yeah, no, I think we're all good there.
Okay, good. Yep. So then we got a couple of questions at least. That's good. And yeah, if there are any more, I see there's one that we didn't get to. What if the data only available for below the saturation pressure? Can it be used on the basis for simulation? Yeah, this is a very important point here. And I actually had a webinar last week with Crowdfield. We can probably share that as well, the YouTube link. There's a distinction between the composition that you use for what we call fluid initialization, which is trying to say what's down there in the reservoir, versus fluid model development. So for fluid model development, the only thing we care about is getting the composition of whatever's in our PVT cell accurately estimated, right? The composition there, and the PVT experiments for that PVT cell. Then we can make an equation of state model, which will hopefully not just work for that one sample PVT cell, fluid, but for the entire reservoir or field, right? So there are methods available to go back from samples that were taken after you go below the saturation pressure to kind of like back estimate what the in situ composition is in the reservoir. And this was presented by Øyvind Fevang in this equilibrium contact mixing paper in the 90s. And we did something similar. I think Matthias Carlsen did something similar in one of his papers for unconventionals as well, right? Where we always, we have such a high drawdown that we can really never do, sampling above the saturation pressure. So if you want to Google something, equilibrium contact mixing is the thing to Google for that. And let's see, is there a possibility?
Oh,
yeah, there's a question about CO2. Yes, so you are able to do swelling tests and MMP type calculations in Whitson PVT for CO2. Yeah, and we have an example from the Volve field, which we're actually presenting in Vienna in 2 weeks' time, where we show the predictions of that, and that's all been done using Whitson PVT. So I'll if I see you there, then we can follow up with that in person, hopefully. I saw there was one comment here about the BO. Let's see, BO should be taken from DL or flash. Yeah, so the oil formation volume factor that you use for your actual fluids in place calculation should be simulated with an equation of state. The BO that you have from the DLE and from the multi-stage separator test and whatnot can be used as an indicator, but it's very important to note that the black oil properties, BO, RS, BGD, little rs, these are all functions of the surface process that you have, right? So if you have two samples, one is got a different surface process than the other, and you're comparing the BOs, then you're not comparing apples to apples. That's why we say you should compare them using a simulation process where they have the same conditions that they've gone from the reservoir conditions to the surface product. I guess the answer is neither. Yeah, but if you're going to use the lab reported data, then you should potentially use this correlation. But that's not. I'm not going to recommend that. So. All right. Yeah. So there's a question. You take a sample from a well already producing via gas lift with a real case. Yeah. So if you have gas lift, then I guess you can try to back estimate, kind of remove the gas composition that you've injected. It's a bit more tricky. It's not something that I'm an expert on. So I'll let Curtis answer that in an email if we're going to follow up on that. So yeah. Got a couple more minutes here. I saw there was something popping up in the Q&A. It's just being a little bit slow here. Can you see that, Jessica?
Well, mine also hasn't updated for 8 minutes. Sorry about that.
So
I don't know why there's a lag in the Q&A there.
Too many hard questions, maybe.
Maybe if you guys have any more questions, put it in the chat box for now. Or feel free to send either Marcus or myself an email, and we're happy to follow up with you directly on any questions that you have for PVT or the Whitson PVT platform itself.
All right, good.
All right. And with that, I will end this off now. Thank you all very much. We will put the recording online, so if you want to watch this again,